Okay, now we will work through the second example of using the discontinuity functions to write the equations for the shear and moment as a function of x. This example is a cantilever beam with a constant distributed load over the first half of the beam and a concentrated moment at the end. First step is to figure out the external reactions. We know that we will have a vertical reaction at the connection point A. We know we have a moment reaction, and we would also have an X reaction, but given that there are no applied forces in X, we can disregard that one. We can consider the distributed load as a single equivalent force for doing our equilibrium equations. Starting with the sum of the moments about point A, we have the moment reaction, which is positive. We have the equivalent force, which is downward and is 100 newtons per meter times 3 meters is the magnitude of the force, and that acts halfway, which is at a distance of 1.5 meters. And we have our concentrated moment out at 6 meters. It is already in the units of a moment. It is already at Newton meters. So the point at which it acts is irrelevant in terms of summing the moments. All of that equals 0. We can solve for the moment at A, and we end up with 300 times 1.5 is a minus 450 plus 150 is a minus 300, or on the other side of the equation is 300 Newton meters. Then taking the sum of the forces in the y direction, we have a positive reaction at A. We have a 300 Newton equivalent force, so the reaction at A is 300 newtons. Now that we know the external reactions, we use all of those to put together the needed terms to write the shear and moment equations. So first, for the shear equation, we start from x equals 0, and we add terms as needed for the external forces that are that are on this beam. First thing we have is a positive reaction at A with a magnitude of 300 newtons. It's a single point force, so we use the first row of the column. For the positive magnitude, we have a plus 300 newtons times the discontinuity term x minus a. In this case, for the reaction at A, x is 0, and we have 0 for the exponent. You can't use the equivalent force for writing these shear and moment discontinuity terms. We have to use one of the terms, use the row in the table for a distributed load. In the table, the distributed load is pointing down, so that's consistent with what we have in this situation. So we have minus W, the magnitude of the distributed load, is 100 newtons per meter, times X minus A, the location that the distributed load begins, which in this case is 0. And we have that term is the exponent is 1. Then the second portion of the term for the distributed load is plus 100 times X minus B, which is the point at which the distributed load stops, which in our case is 3. And then we continue looking to the end of the beam. The only thing left is discounted in this case for two reasons. First of all, anything that acts at the far right end of the beam, the term goes to 0 anyway, but for a concentrated moment, if you look in the second row of the table, for the shear equation, a concentrated moment does not contribute to the shear. So, we have every term that we need. What can we do to simplify? The X minus 0 to the 0 simplifies just to 1. X minus 0 to the 1 simplifies to X. So we can say that our equation for the shear is 300 newtons minus 100 newtons per meter times X plus 100 newtons per meter times X minus 3 to the 1. That is the moment equation. Notice what the units will do to simplify out. The first term is simply newtons. The second term is newtons per meter times the distance x in meters. We'll simplify to newtons, and the same for the third term. So your units on your shear equation, as should be, is newtons. For the moment equation, we're going to have a few more terms going on. For the first one, we look at the single concentrated force. We have the reaction at A is a positive, so the moment term out of the first row in our discontinuity table is a plus P. Discontinuity term X minus 0, the location that it acts, this time with a 1 exponent. Then we also have at X equals 0 the moment reaction at A. If we look at the second row in the table, we have a counterclockwise moment in the table, corresponds to a minus m sub 0 term for the discontinuity term. That matches the situation that we have, so we'll have a minus ma x minus a equals 0 to the 0. We then need the term out of the final column of the table in the third row for the distributed load. So minus W over 2 X minus A squared plus W over 2 X minus B squared. Substituting in the values for these, we have plus 300 x minus 0 to the 1 simplifies to 1. The value of the moment at A was 300 Newton meters, so we have minus 300 x minus 0 to the 0 simplifies x minus 0 to the 1 simplifies to x minus 0 to the 0 simplifies to 1. So we have 300x minus 300 minus w divided by 2. The magnitude of the distributed load W is 100, so we have minus 50 x minus 0 to the 2 plus 50 x minus 3 to the 2. Simplifying yet again, 300x minus 300 minus 50 x squared plus 50 times the discontinuity term, x minus 3 squared. Simplifying, or rather sorting, in increasing powers of x, minus 300 plus 300x minus 50x squared plus 50 x minus 3 squared. The third example that we have for using discontinuity functions to write the shared moment equations is a non-constant distributed load. As always, the first thing we have to figure out is what are the external forces acting on our structure. We're going to have a reaction at A, we're going to have a reaction at B, and it's just a little bit trickier to figure this out. For a triangular force, we know that the point of action for this force is going to be 1/3 from the large end or 2/3 from the small end, and the equivalent force is essentially the area under the curve. So we've got 1/2 times 60 newtons per meter times the overall distance of 9 meters. And with that, we can write our equilibrium equations to figure out all of the reactions. For the sum of the moments about A, we'll have a term for the reaction at B, so plus 6 meters times the reaction at B. We'll have a negative term for the equivalent force, for which 1/2 times 60 times 9 is the magnitude of that force, and its point of action is at 3 meters. And we'll also have a term for the concentrated load at the end of the beam, also a negative 40 newtons at that distance of 9 meters. Simplifying out, we see that the reaction at B is 195 newtons. Taking that into the y equilibrium, we have a positive RA plus 195 newtons minus the equivalent force from the distributed load, and we see that RA has to equal 115 newtons. Now that we have all of our external reactions, we use our handy-dandy discontinuity term table and add terms for each of the external forces that we have. We know our reaction at A is a positive 115. So writing the shear equation, we need a plus 115 times x minus A. For the reaction at A, that's active at x equals 0, and that gets an exponent of 0. Now we have to go into the bottom row of the table for the linear distributed load. For that, we need to figure out what the slope of W is. K is the slope of W, and for that we need the value of W at B, which is 0, minus the value of the distributed load at A, which is 60, over the location of B, which is 9, minus the location of A, which is 0. So we have a slope of minus 60 over 9. A slope of minus 60 over 9. Alright, technical difficulties. Starting at the point where we know the two reactions are 115 newtons and 195 newtons. Now we put together the terms for the shear equation, starting with the the left reaction, 115, x minus 0 to the 0, minus 60, which is the magnitude of the distributed load at the beginning, x minus 0 to the 1, plus 1/2 times 60 over 9 times x minus 0 squared plus 195 x minus 6 to the 0. This is the term for the reaction at B, and we did not write the term for the 40 Newton force because it's all the way at the right end. The right end is ignored. For the moment equation, we start with the reaction at A, which is 115 newtons, times x minus 0 to the 1. We then need the term for the beginning of the distributed load, which is a minus 60 newtons per meter divided by 2 for the first term in the moment equation for in the bottom row of the table. X minus A equals 0, and that term is squared. Then we have the minus k over 6 x minus A term. The slope k is 60/9, and we need to divide that by 6, so we add another 6 on the denominator. And where does that is an x minus A term. A is 0 because the distributed load starts at x equals 0, and that term is cubed. We then need a concentrated force term out of the first row of the table, plus 195 x minus 6, and that term is to the first power. Again, like in the shear equation, none of the terms of the moment equation that deal with the x equals b end, or the term for the 40 Newton force, none of those contribute because they're at the right end of the beam. So these are all the terms that we have. We know that x minus 0 to the 1 simplifies to x. We know that x minus 0 to the 2 simplifies to x squared. We know that x minus 0 to the 3 simplifies to x cubed. Up here in the shear equation, we know that this simplifies to 1, this simplifies to x, this simplifies to x squared. So rewriting both of them in simplified form, we have the shear equals 115 minus 60x plus, that simplifies down to 10/3 x squared plus 195 x minus 6 to the 0. The moment equation simplifies to 115x minus 30x squared plus 10/9 x cubed plus 195 x minus 6 to the 1. So essentially, to sum up the process, it all starts with a free body diagram, find the external reactions, and then use the table for the discontinuity terms to put together and then simplify the equation for the shear and the moment, internal shear and moment as a function of x for any loading situation.